And we are recording. Okay. So, the stuff we start today is actually going to be the basis of all of our explanations for the remaining stuff for the year. So today is like the foundation, and then next week we get a little bit more into the weeds, and then I am going to hold a class that Tuesday of the last week on the 26th. So that'll be our last class will be on the 26th. So this is our fourth to last class, and then we got two next week and then one the final week. So we're close to being done. So we're all going to be talking about attractions this week, and next week, and et cetera, et cetera. The problem with attraction is that you can't really see attraction between charges unless you do a whole lot of playing with static electricity. So we're going to start off actually talking about magnets, because we're familiar with magnets and you're used to seeing how magnets work. It's something we can actually visually watch. And then we'll understand that the same things that dictate the behavior of magnets dictate the behavior of our particles. And so hopefully that will help everything make sense as we then start trying to go over what else is going on in the periodic table. So we've been talking about the periodic table, the arrangement of the periodic table. We know it's telling us stuff about electrons and electron configurations and valence electrons, and that's all very great. There's a whole lot more information, however, that is on this periodic table that's based on attraction and whether or not an element experiences a high amount of attraction for its electrons or a low amount of attraction for its electrons. So what we're going to find is that on top of this periodic table, we're actually going to be able to write things like, well, atomic radius goes down in this way, right? So radius gets bigger this way, and it's just going to be like a big long trend that way. And oops, backwards, damn it, go backwards. Come on. So we're going to be able to say things that we've got stuff like actual size of elements that goes one way, and then I'm going to throw out these other terms like electronegativity, which is an incredibly important property and actually is the thing that tends to dictate most chemical properties is electronegativity. And we'll find it's like, but wait a minute, electronegativity goes exactly the opposite way. So why is that? And the reason is because of attraction. So first we need to be able to explain attraction, which is what we're going to do today first. So I want to play with some magnets first. That's why I hooked up the document camera, because as I said, we can't really see the attraction between electric charges because they're too small. Like electrons and protons are tiny, so I can't actually see them. But magnets behave in the exact same way and are going to allow us to be able to see that sort of interaction. So I'm going to play with magnets and cardboard. And these are your standard, let's see, stop sharing. These are your standard regular ceramic boring magnets. There, I spelled it in my video. Okay. Okay, so I've got your standard magnets. I think I got these from Amazon for like 10 bucks for 200 or something like that. So, you know, a magnet has a side to it, right? It's got a north and a south. And that if you have the two of them together, they like to attract. But if you have a north and a north or a south and a south, they're clearly repelling. And if you've never played this game with magnets, you're missing out, or you're cooler than I am. I don't know, but you can make magnets chase around because they do repel. So we have the same sort of thing where you've got opposites attracting and like charges repelling, just like we do with charges. So there's more than just opposites attracting and like charges repelling. There is several things that make a difference as to how these two magnets are going to attract. So you know that you can't necessarily stick a single magnet on your refrigerator and have it hold all of those stupid takeout menus. Because at some point you reach a critical amount where it's too many pieces of paper to try and hold up. So if you take that in mind, then we're going to imagine that these thick pieces of cardboard, right? This is good corrugated cardboard, are like our stacks of paper. So I'm going to put a single magnet on the ground here. And, right, so clearly it's going to go that way. But if I put a single piece of cardboard, I can get some attraction, right? But what should happen as I put more and more cardboard between these two magnets? What's going to happen when I stick this next one on?
It's not going to jump up.
It is not going to jump up. I'm still going to get a little, but it's definitely not very strong. I think that is that's kind of the state of most people's precarious stack of takeout menus from the refrigerator. I think exist in that level of state where if somebody walks by, then it's all going to come falling down. So, but if I keep putting more and more on, well, now I've got really nothing. Okay, so what we imagine is that these pieces of cardboard are representing distance. They are spacing these two magnets apart. And in fact, if you've ever held magnets together in your hand, then you know that you can actually feel the attraction between them, and that attraction is stronger when they're closer, and it doesn't really exist when they're far apart. So that's what these are representing. Distance matters for attraction. So that's number one. Number two is I have a whole lot of magnets. And the question is, does the matter of the number of magnets make a difference with my attraction? And I think you should be pretty obvious in thinking that, yeah, I think it does. So I'm going to stick with 3 levels again. I'm going to start off with my 1 magnet on the bottom and 1 magnet on the top. All right. And I did get some attraction here, but it was like, it was a little loosey-goosey. But if I increase the number of magnets on each side, so now I've got 2 magnets on one side, and I stick 2 magnets, so now I've doubled the amount of charge, right? So I've got double the magnets, so I should have double the attraction here. And I do. This picks up much, much easier. And if I stick another magnet on each, now I've tripled the amount of attraction, right? So I've got 3 and 3, so this should be even easier. And it is. It picks it up much faster. It holds it much stronger. And if I keep going, 4 and 4, and what I'm going to want you to do is imagine that instead of 4 magnets down here and 4 magnets in my hand, that this is like 4 protons in the middle of an atom, a bunch of distance because my atom is mostly empty space, and a bunch of electrons on the outside, and that those are like, okay, the more of those I have, the more attraction I have, and they're going to stick together. So there is a difference here that the amount of stuff you have attracting is also going to matter. All right, so we can pretty easily show with magnets that we're going to focus on distance between the attractive things, and we're going to focus on the amount of things that are attracting. So now let's switch back. All right, so I'm going to switch over to these notes. This was the second set of notes that was attached to the participation. And these seem kind of large, but they're not really. It's mostly because there's big pictures. So All right, so let me switch over. Okay. And then let me do a quick recap because people popped in. If you snuck in, I still don't see Ashton, Kamaya, Sophia, Allison, Ashira, Manny, Nina, Ariana, Eliora, Dalia, Jayla, and Jada Spriggs. But I think I got the others who came in late. Okay. So we have a specific term here for the kind of attraction we are talking about, and it is Coulombic attraction. And the reason it is called Coulombic Attraction is because it's named after some French guy who I don't actually know his first name. I know his last name is Coulomb. And he did a bunch of stuff with electric charges, and they talk about him both in physics and in chemistry, this law of Coulombic attraction. So, but for us, it is specifically the attraction between opposite charges. Because I am assuming you recognize that opposite charges attract and like charges repel. But the protons, which of course are positive, that are in the nucleus have an attraction for the electrons, which are negative, that surround it. Now, it's kind of helpful here to think about who's bigger. So while protons and electrons have the exact same amount of charge, they are not of equal physical size. So who's bigger, a proton or an electron?
Proton.
Proton. Proton is bigger. So who's doing the attracting then? Is the proton attracting the electron and pulling it in? Or is the electron attracting the proton and trying to pull it out of the nucleus?
The proton attracts the electron.
Yes. All right. So I just want to say down here. All right. So the proton is pulling the electron in. That is always the direction of our attraction, is always in. Okay. That's what keeps an atom actually together. So our attractive force can be strong or it can be weak. So we can think of it as being strong, like, you know, those really fancy, expensive neodymium magnets that are like tiny but super strong, or they can be weak, like the pizza carry-out magnet that is basically like some paper with the small magnetic backing that hardly sticks on your fridge. So just because you're attracting, it's not all equal. So there are two factors that are going to control our attraction, and we kind of just briefly saw them with the magnets. So factor number one is distance. Okay, so I've got this image, and I'm showing here that I've got a single, right? I've got a single proton, and then I've got a single electron, and I am spacing them out at various different distances, and then measuring the force of attraction here. So in this situation, what is the independent variable? What am I actively adjusting in this diagram?
Distance.
Distance. Okay, I am actively controlling what the distance is. So what seems to be the dependent variable? What is changing based on changing the distance?
Force of attraction.
Force of attraction. Okay, so what seems to be the relationship here? What happens to the force of attraction when I change the distance?
It's inverse.
They have an inverse relationship. Okay, meaning a greater distance leads to a weaker force of attraction, and vice versa. And if you've ever held two magnets in your hands, you know that is the case. So the question here is, if the distance between a proton and electron is 0.50 nanometers, the force of attraction would be greater than or less than the 0.26 times 10 to the negative 8. All right. So if I was 0.50, is my force going to be greater than or less than the 0.26?
Less.
It's going to be less than. All right, because a greater distance is a weaker force. So 0.50 is greater than the 0.30. So therefore, the force of attraction is going to be even less than the 0.26. All right, if you need a picture of that, take a picture because I'm going to scroll up. All right. Okay, so taking that concept and actually looking at the periodic table now, I've got these three elements. Are these in the same group or the same period?
Group.
Group. And they all happen to be in group 1, but they are in the same group. So which of these elements seems to have the greatest distance between them?
Potassium.
All right. So potassium seems to have the greatest distance between the nucleus and the valence electrons. So when we are talking attraction, we are always talking about the attraction to the valence electrons. That is potassium's little valence electron. And the reason that it has the greatest distance, you can literally say, is the number of shells. All right, potassium has 1, 2, 3, 4. So potassium has 4 shells. Sodium has 3. And lithium has 2. And again, you can think of them as shells or energy levels, doesn't matter. But every time you add another shell, it adds another layer. It makes it bigger, okay? So if potassium has the greatest distance, what does that mean for its attraction? Should it be the greatest or the smallest? The weakest?
Weakest.
All right, so it's gonna have the weakest amount of attraction as shown, and it shows you that it has the weakest attraction because it's got the skinny little arrow, all right, by the skinniest arrow in the diagram. So you can think about potassium as this big, relatively speaking, this big, huge element. It can barely hold on to its little electron because it's reaching out so big. It's so far away, its little attractive arms can barely hold on to that valence electron because it's stretching around so many shells. So cesium is even farther down. So right below potassium is rubidium, and below rubidium is cesium. So if potassium had 4 shells, well, rubidium would have 5, so cesium would have 6 shells. And if it has even 6 shells, so you can imagine it's got another 2 circles around here. So if it had all of that, is it going to have more or less attraction than potassium?
Less.
Less. All right? Because it's bigger. And for us, bigger in number of shells or energy levels means less attraction. So hydrogen is actually up here, right? So hydrogen would be up here. It's above lithium. And hydrogen only has one little shell. So if it's only got one tiny little shell, what does that mean for its attraction in comparison to lithium? More. Okay. So to summarize, when we're talking about on the periodic table, elements at the top of the periodic table have stronger attraction between their protons and electrons than elements at the bottom. All right, so elements at our top of the periodic table in the first couple of periods have a lot more attraction than the elements all the way at the bottom in periods 5, 6, and 7. That should make a little bit of sense. This is the concept that is much easier to think of because the difference in size here is really striking. So if you need a picture of that, take a picture of that because we're about to switch pages. Okay. So the next one, this is our second factor, the amount of charge. So this is like when I kept putting more magnets down on the table and more magnets in my hand and increasing the number of magnets. So here we're still talking about dealing with one valence electron, but now we have different amounts of protons here. So in this instance, what are we actively changing? What is our independent variable?
Number of protons.
Number of protons.
Number of protons. And then what are we measuring based on that change?
Force of attraction.
Force of attraction still. And what seems to be our relationship here? As I change the number of protons, what is happening to my force?
It's a direct relationship.
This is direct, meaning a larger amount of protons produces a larger force of attraction. That should also kind of make some logical sense. If I have more things to attract, they have more attraction. Okay, so I've kept my distance the same all the way across. So that's really the only way you can measure that is by making sure that that distance stays the same. So if I had 5 protons here, so 1, 2, 3, 4, 5. All right, so if I have 5 protons present, what do we think the force of attraction would be? Like what actual number? If that's for 1 and 2, and that's 3, and that's 4, what do we think 5 would be?
Same thing. 10.50.
Right, so we're gonna multiply that by 5. And so 5 times 2 is 10, but the 0.3 times 5 is 1.5. So it would be 11.5 times 10 to the negative 8th, which is actually 1.15 times 10 to the negative 7. So literally, we just multiply the force of attraction by the number of protons. So that is just a proof of concept. That is not an actual calculation to do. That's just a, oh, so The more I have, the more I have. Got it. All right. So it says the attractive and repulsive forces in an atom are complex because an electron is attracted to the proton, but it is also repelled by the other electrons that are in the atom. So we actually have two forces going into play here, but the attractive force of the nucleus is not divided up among all the electrons. So it's not like if I had 2 electrons out here, they would each get half of this amount. That is not the case. So each electron gets approximately the same attractive force of the nucleus. So I'm going to scroll up if you need a picture. Because what we have here is, like showing in this diagram, you've got an electron out here, an electron out here. Each of them receive the same amount of force of attraction. It doesn't matter that there's 2 of them. They don't split it. The amount of attraction is the same, even if we start adding extra electrons. So that doesn't actually play a part. It's more just the raw number of things in the nucleus that are doing the attraction. Okay. So now let's look at these elements.
Can you scroll up a tad bit, please?
Yep.
Thank you.
Mm-hmm. We good?
Yep, thanks.
Okay. Okay. So now let's look at these. So I've got sodium, aluminum, and chlorine. These elements are in the same group or the same period?
Period.
Period.
They're in the same period. All right, so I've got spaces here for us to write down the number of protons of these things. So how many protons does sodium have?
11.
All right, so we can imagine there's like a little plus 11 in the middle of that thing. And what about aluminum?
13.
All right, and lastly, chlorine?
17.
17. Okay. So if I look at these 3 elements in this same period, they kind of look the same when I look at the diagram, right? So I've got sodium's got 1 electron out here, and aluminum's got 3, and then chlorine's got 7 in its valence shell, right? So it's got 1 valence electron. This guy's got 3 valence electrons. This guy's got 7 valence electrons. So they essentially are the same size because they have the same number of shells. So the distance from the nucleus to the valence electrons is basically identical. There are some small variations, but it is not at all obvious the difference in size here as it was in that first set of elements when we were looking at elements down the group. So if these guys are not really different in size, well, then that means that there is something else that is giving us these differences in the sizes of the arrows. And the arrows would indicate that who is doing the major amount of attracting here. Who's got the most attraction between sodium, aluminum, and chlorine?
Chlorine.
Chlorine, all right? The arrow on chlorine is the biggest one. From the previous diagram, arrow, the size of the arrow represents the attraction. So we're going to say that chlorine seems to have the greatest amount of charge between the nucleus and the valence electrons because of the number of protons. This means it has the greatest amount of attraction as shown by the thickness of the arrow. Okay, so if we were imagining argon in this set of elements of sodium, aluminum, and chlorine, argon would be over here, right? With its 1, 2, argon would be over here. And how many protons does argon have?
18.
It's got 18. So with its 18 protons, is it going to have more or less attraction than chlorine?
Less.
More.
It's going to have more. All right, so here, more protons equals more attraction. All right, so if you need a picture of that, snap a picture, and then I'll switch to the last page. Okay, and then it's saying magnesium. Well, how many protons does magnesium have?
12.
Got 12. Okay, so it wants us to compare the attraction of magnesium for aluminum from the previous page, which had 13. So is magnesium going to have more or less attraction than aluminum?
Less.
Less. Okay, so which side of the periodic table seems to have stronger attraction? The left side or the right side?
Right.
The right.
The right. Okay, so the right side of the periodic table has stronger Coulombic attraction between the protons and electrons and elements on the left. Okay, so once you kind of remember who is beast for attraction, top and left, then everything we're going to talk about next week is going to make sense. So you're like, okay, so top left is where everything likes attraction, super strong attraction, and bottom, I keep saying top and left. Top and right is where everybody has super, super strong attraction, and bottom and left is where like they have no attraction whatsoever. It is going to be super helpful next week when we start talking about all these other stuff. So this equation here, which they do calculations with in physics, but we don't do calculations with, this formula is called Coulomb's law. So the F is force of attraction. The K is a constant that I don't remember at all because literally I have not done any calculations with this formula since I was in college, because we don't have differences of charge really in chemistry. Everything is the same unit of charge. A proton and electron has the same amount of charge, whereas in physics they have variable amounts of charge. So they do more stuff with this than I do. Ratkoff will go off about Coulomb's law. So Q1 and Q2, those are the two charges. And R, if we think back in our geometry, is a radius distance, all right? It's a distance. So if you look at the equation, it tells you, what did we say had a direct relationship? The charges. They have a direct relationship, and that makes sense because they are in the numerator of this equation. And what do we say had an inverse relationship? The distance, which would make sense because it's in the denominator. So again, I'm not ever going to have you do any calculations with this equation. It's just another way to drive home that the mathematical relationship matches what we saw because of where those variables are in this equation, that numerator versus denominator relationship. So if I look at this, I've got the Q1, Q2 here, and those are multiplied together. And then I've got this distance factor that is squared. Which one of those seems to be a greater factor? The amount of charge or the distance?
Distance.
Distance, because it's squared. All right, the distance is a greater factor on the force of attraction than the amount of charge. And that is going to hold true with everything that we are talking about. You find a larger amount of difference in various properties up and down a group because the distance is playing a larger factor in my attraction than my left to right difference in charge. Okay, so that's just kind of piecing that all together. So if you want to take a picture of that, and then I'm going to scroll up and we'll make some notes on this little periodic table here. Okay, so to start off with, you need to remember and imagine where the elements with the greatest and the weakest force of attraction are on this periodic table. So the greatest amount of attraction between protons and valence electrons is where? Top, bottom, right, left.
Left.
Top right.
Top right. So over here, we're going to say this is the greatest attraction. And in fact, we will be talking about helium and fluorine a lot in terms of attraction. In fact, it is this thing, this greatest attraction, that is going to start explaining why fluorine does what fluorine does. But our weakest forces of attraction are on the exact opposite part of the periodic table. So our weakest attraction is over here. This is also going to start explaining why my alkali metals over here lose an electron so easily. They have weak attraction for their electron. So it makes it easy to lose it. So everything next week is going to be either towards the bottom left or up towards the top right. So when you need to identify who's got a stronger attractive force, you literally just need to see where they are on the periodic table and pick the one that is closer to the top right is going to have the stronger attraction. So between barium and calcium, if I remember correctly, calcium is there and barium would be there. So who's going to have the stronger force of attraction between those two? I just heard the EM.
Calcium.
Calcium. All right, because calcium is further up. So between chromium and copper is right here and chromium is right here.
Copper.
Copper, because it is further to the right. So between argon, which is a noble gas about there, and xenon, which is a noble gas down there, which one's going to have more attraction?
Argon.
Argon, because it is higher up. Gallium and bromine. Gallium is that guy. Bromine would be that guy.
Bromine.
Bromine, it's further to the right. Arsenic and phosphorus. So phosphorus is here, arsenic is here.
Phosphorus.
It's further up. And selenium and chlorine. Let me switch colors here. So chlorine is going to be here, and selenium there.
Chlorine.
Chlorine, and it is both right and up. It is both of them, right? It's further right and it's further up. Let's see here. So take a picture of that, because that's the end of these notes, and then I want to
Miss
switch up.
Baskin,
Yes,
can you slide up just like a tiny bit? Wait, I mean the other way.
the other way, you mean down?
Yes.
Like that?
Yes, thank you.
I love that. By up, you mean down? Yes, I can do that. You need some coffee too? Okay. Let me switch back. Okay, so for this Sunday, if you have not done video 33, do video 33. That's the crash course on the periodic table. Exit ticket will be on the next screen. So again, the ed puzzle and the exit tickets get you your full participation credit. So it should be a 10 out of 10 for that. The quizzes is a completion grade this week, but you should do it after you watch the periodic table video, and make sure you have your periodic table with you. That's highly helpful to be able to do that quizzes. That link is in Google Classroom. So the last thing to do for the week is this simulation activity that is listed as a Google Doc in Google Classroom under the week 3 practice and application. So it's a simulation activity that basically has you do the same thing that we just walked through with the notes, except it actually is a little, I think it's a HTML applet, or it might be a Java applet, or a Flash applet that lets you change the amount of charge and change the distance and then record the force of attraction. So it is asking you to identify independent and dependent variables. It's asking you to essentially set up your own experiment and then provide some explanations. So you should have these notes in front of you when you do that, because it'll give you guidance about what to set up. So there's no listing about how to set up the amount of charge and the distance. Like you get to choose all of that stuff, but you can use these notes as a guide for how to get started. If you have any problems with it, by all means, please let me know, but you should be able to type in your data and then write down your explanation. So it's pretty easy. And I didn't do extra credit this week because there's going to be extra credit the last week. And that's it. So there is your exit ticket.
Did you send it in the chat?
I'm typing it.
Thank you.
Sorry, my cat was stretching in the corner and it was really cute. All right, so there you go. So once you get that exit ticket, unless you have any questions, you are good to go, and I will see you next week.
Miss Baskin, have a good day.
Thank
Weekend.
you.
Bye, Miss Baskin.
Bye, guys.
So, Ms. Baskin, does the attraction, like how high or low like the amount of attraction between the proton and like the electron due to kind of the grouping influence how when it becomes an ion. So there's less attraction on something, so it has the easiest time becoming an ion because that electron is easily removed.
Correct. Absolutely.
Okay.
And it also then dictates which ones become positive ions versus negative ions. So you'll notice all of my negative ions are on that greater attraction side.
I noticed that.
Yep.
I found that interesting.
Yeah.
Have a good day.
Thank you. You too.
Can you send a picture of your cat in the remind?
Sure.
Yay!
She is my Catherine's sister lived in Africa for a couple of years. Don't ask. But she sent us a stuffed crocodile, and my cat snuggles with the crocodile.
Oh.
And it's kind of the cutest thing. So she's really adorable. And she snuggles with the crocodile, and it makes me laugh. Otherwise, she's very, very skittish.
Yes.
She's like, who are all these people?
Have a good day.
Thank you. You too.
Thank you.